Hello, everyone, and welcome to multivariable calculus. Actually, in this chapter, the main object that we're going to study are real valued functions of two variables. So function of the forms, two numbers are going to come in, two inputs are going to go inside that function f, and then something will happen to those two numbers, and then the function will spit out only one value, only one real value. So two inputs, one outputs, real valued functions of two variables. And those are going to be the main objects studied in this chapter. So let me read the actual definition for you. So a function f of two variables is a rule of assignment from a subset of the Cartesian plane, so a subset of R2. That subset, of course, is going to be the domain of the function, where the function is actually defined, to a subset of the real line. And here it's really, really crucial to be a function that this rule of assignment assigns a unique number to a pair of numbers inside the domain. So there's only one output for one pair of inputs. If not, this would be just a correspondence or a relationship. But here we want a function, so only one output. And a little bit of notation here. So since f takes a value in the real Cartesian plane, so it's going to go from the Cartesian plane to the real line. So it's from R2 to R. In one variable calculus, all our functions were of the form from R to R. Now it's going to be from R2 to R. And so the set of all inputs are in R2 and the set of all outputs are in R. So there's two inputs and only one output. And these are going to be the objects that we're going to study together in this chapter. So a bunch of examples. I have two functions here, functions defined algebraically. So let f of xy be equal to 2x5 y squared minus x cubed minus y4 minus 5xy plus 1. So that's an example of a function that depends on x and y. So give me any number in the real Cartesian plane. The domain is obviously everything here. There's no division by zero. There's no square root. There's no logarithmic. So this function is defined everywhere. So if you give me a pair of numbers, I can compute an output thanks to this formula. And I also have the function g, which is y squared times the logarithmic of x cubed plus y4. So here, the domain, you have to be careful. There's values that are such that y cubed plus y4 are either 0 or negative. So this is not defined everywhere. But for those pairs where it's defined, then you can compute the output algebraically. And all the functions that we're going to study in this chapter are going to be defined algebraically. So in the sense that we're going to be dealing with equations in this chapter. All right, let's do an example. Let's compute the domain of the function f of xy equal to x ln of y plus 1, all that divided by x squared plus y squared. And just to get used to the actual notation, we're going to compute the output at 2, 1. So we're going to compute f of 2, 1. Actually, let's do the computation of the output. That's probably the most straightforward thing to do. So here, when you are asked to compute f at 2, 1, you need to understand that the 2 here is the x value. So every single occurrence of x is going to be replaced by 2, and then you're going to replace every single y by 1. And now what do you get? Well, you get 2 times ln of 1 plus 1 divided by 2 squared plus 1 squared. And then if you simplify, 1 plus 1 is 2, so you have a ln of 2 at the numerator. You have a 2 that multiplies that ln of 2, and all that is over 4 plus 1, which is 5. So you have your output. So just be careful. Just replace the corresponding x's by 2 and the corresponding y by 1. Just be careful, evaluate, use your calculator, or simplify depending on your skills. Now for the domain. The first thing that I can see in this question is there's a denominator. So as soon as you have an expression where there's a bunch of denominators, you need to make sure that these denominators cannot be equal to 0. So when I look at my first restriction, my division by 0, when is x squared plus y squared equal to 0? Or if I want to be more precise, we don't want x squared plus y squared equal to 0. So the only way this can happen, because x squared is greater or equal than 0, and because y squared is greater or equal than 0, the only way x squared plus I squared is going to be equal to 0 is if and only if x and y are both equal to 0. So if you try to evaluate this function at 0, 0, you're going to create a division by 0. So here, the origin of the Cartesian plane is not, for sure, it's not inside the domain. So we have to kick that point out. So that's for the denominator. There's no square roots or even roots, but there's a logarithmic term. So when you have a logarithmic term, you have to be careful. The logarithmic function cannot swallow a 0 or something strictly negative. So the inside of the logarithmic term needs to be strictly bigger than 0. So here, the inside of my logarithmic term is y plus 1. So I want y plus 1 to be strictly bigger than 0. Then if you isolate y, you get that y needs to be strictly bigger than minus 1. So now the best way to illustrate the domain is actually by picturing it with a subset of the Cartesian plane. So here in my example, I've done it in blue. So the first thing I did to get that domain finalized, I actually drew the equation y equal minus 1. Because my inequality is strict, I know that line is not going to be inside the domain, so I use a dashed line to say that if you are on that line, you're not within the domain. But if you're above it, you're fine. So if you are a point in the Cartesian plane where your y value is strictly bigger than 1, you're fine. But you have to be very careful. You don't want the origin, and the origin does fall within that region. So you need to remove the origin from that zone. So here, every point above y equal 1, strictly above y equal 1, but the origin, so I drew a white dot there to remove or to punch out, like this point. So everywhere in the blue region is a point in the Cartesian plane where the function is defined. So the best way to represent a domain for a function of two variables is by coloring, the region where the function is defined. So here, above, strictly above y equal minus 1, but you need to remove the 0, and that's your beautiful domain. So again, here, my two restrictions combined is how I get my little blue zone. All right, let's do another example. Next example. So same idea here. Let's compute the domain of f of xy equal to 1 plus the square root of x plus y plus 2. And also we want to compute the output of the function at minus 1, 8. So here again, I'm going to start with the output computation. So here, I'm going to replace minus 1 everywhere. In my equation where x is, there's only one x inside the square root. So x is going to be replaced by minus 1. And then the y is going to be replaced by 8. Now, if I compute the output, I get 1 plus the square root of minus 1 plus 8 plus 2. Minus 1 plus 8 plus 2 is 9. Square root of 9 is 3. 3 plus 1 is 4. So I get my output. No problemo. Now, what about the domain? So here, there's no denominator. There's no logarithmic term, but there's a square root. A square root is defined if the inside is 0 or strictly positive. So in other words, you cannot have something strictly negative inside a square root. So the difference between a square root and a logarithmic term, the inside of the square root can be bigger or equal to 0. Meanwhile, a logarithmic term needs to be strictly bigger than 0. So here, because I have a square root of something, I want that something. So I want the interior of that square root to be bigger than 0, bigger or equal. And here, my advice is to always play with this inequality until you see an equation of something that you know that you're familiar with. So here I see a linear equation with respect to x and y. So I'm going to isolate y. So I'm bringing the x on the right side as minus x and the 2 on the left, on the right side also as minus 2. So y needs to be bigger or equal to minus x minus 2. So I find here the best way to do this is to draw that line. So here for you, I drew the line y equal minus x minus 2. So the y-intercept is minus 2 and the slope is minus 1. I use a full blue line here because the inequality is inclusive in the sense that if you are a point on that line, the square root, the inside of the square root is going to be 0, which is fine. So here, the border of that domain is included, like unlike the previous example, because the inequality is inclusive. And then because y needs to be bigger or equal, I'm talking about the region that is above that line, and I've shaded that region here in blue for you. So here, just make sure that you understand the difference between using a dash line when the border is not included and using a full line when the border is included. And for us, at this level of calculus, typically the distinction is going to be between a logarithmic term or a square root function, where inside the logarithmic term you cannot have 0, but for a square root function it's fine. Okay, and of course if you have a division, if you have a denominator, then you need to remove it. And typically when you remove stuff, you use a dash line to visually represent that process. But anyways, so here's my domain. Again, the best way to represent the domain of a function of two variables is by coloring the region of the Cartesian plane where the function is defined. All right, let's do one more example of a domain computation. All right, let's do one more example of domain computation. Let's compute the domain of f of xy equal to 1 over y ln of x. So a lot of action here. We have a denominator, we have a logarithmic term, so we need to find all the pairs in the Cartesian plane where this function is defined. So it's always kind of easier or simpler to think about where does it crash, and you remove those points. So the first thing I'm going to do here, I'm going to start with the fact that I have ln of x, like a simple ln of x, where I have x inside here. So I know ln of x on its own is such that the x value needs to be greater, strictly bigger than 0. So because of the ln of x, which is ln of something here, I know the x value needs to be strictly bigger than 0. So it does not matter what pair of point you're giving me, as soon as the x coordinate, as soon as the input x is 0 or strictly negative, it's going to crash. So it needs to be strictly bigger than 0. So the first thing I did here is I drew the line x equals 0. And I know on that line, all those points in the Cartesian plane, the x coordinate is 0, it will make this function crash. So I drew a dashed line. I know that this is not going to be part of the domain. And because my inequality is strictly bigger than 0, I know that I need to only consider the point on the right side in the blue zone. So anything on the left side, if the x coordinate is 0 or strictly negative, so here in white, none of those points for sure are inside the domain. So what about now the denominator? So at the denominator, I have two terms. So you just need to do it case by case. So I have y here, and I have also that famous ln of x. So those two terms could create zeros for me. So if I start with y, I don't want y to be equal to 0. So what I did next is I drew the line y equal to 0. And I know on that line, it's not going to be defined, because as soon as you pick a point where the y coordinate is 0, you're going to create a denominator that is equal to 0. So I drew that dashed line. I only drew it in the blue zone because I know on the white side it's not defined. So I'm removing that dashed line on the blue zone. And now the trickier part, or the trickiest part of this question, is we don't want the logarithmic term. So we don't want the logarithmic term to be equal to 0. So you need to remember here that when the inside is equal to 1, the logarithmic of 1 is equal to 0. So ln of x, if you don't want ln of x to be 0, then you don't want the inside, in this case it's just x, you don't want the inside to be equal to 1. So here what I did is I drew the line x equal 1 with a dashed line. Any point on that line, on that red dashed line, that vertical line x equal 1, none of those points are inside the domain. So here, the domain in blue for that function is everything on the right side of x equal to 0, but I had to remove the portion y equal to 0, so the x-axis in that blue zone, and also the vertical line x equal to 1. But anywhere else, like we have like kind of 4 region now in blue, my function is defined. Again, the best way to represent a domain for a function of two variables is with a nice little pictures. Of course, with colors, if possible. We like to dream in colors. Anyways, for that first video of function of two variables and their domain, that's it. That's all. Bye-bye, là.